Hey everyone, welcome to another session of Ceerazzledazzle Physics. In today's session, guys, we're going to be doing a full GCSE Physics past paper. Today we're going to be looking at Paper 2 AQA GCSE Physics Higher Tier 2019. This paper will take us 1 hour and 45 minutes. Obviously, make sure you've tried the paper before watching me do it. You should just watch this video to look at my thinking and understanding of how I tackle the questions. Okay, so let's get straight into it. Figure 1 shows the parallel rays of light being refracted by a convex lens. What is the distance x called? Right, the distance between the lens and the focal point over here, this is called the focal length. This is called the focal length here. Okay, and also if you're struggling in any of these questions, if you look at the description, I'm going to put in my videos for every single question so that you can revisit the content if you get stuck. Because obviously in this lesson, I'm just going to go through the paper, but if you need to understand the content, you just watch those videos. 1.2, lenses can be used to form part of an image. Right, complete the ray diagram in figure 2 to show how a convex lens forms an image. Right, so we've got this ray diagram over here, so you've got to complete the diagram. I need to use the computer to do this. Obviously you're going to be taking out a ruler. We're going to be we're going to insert a shape right now. So for me, I'm going to draw one ray of light now. Don't forget, so we've got one ray of light going horizontally across, then going for the focal point. You've got to also add a line going directly through the center of the lens. Yes, from the top of the object, directly through the center of the lens. And over here, where they both cross, this is going to be where the image is formed. So I'm going to draw where the image is formed right now. It's over here, so image is now formed over here. There we go. So taking a ruler, we're drawing this out, and this is the image. The image is formed over here. So this is the arrow used to represent the image. So the image is formed over here. Next one, it's going to be, let's go for figure 3 shows how a concave lens forms the image of an object. Give one similarity and one difference between the image formed by the convex lens and the image formed by the concave lens. Right, so this is the concave lens. The first thing we can notice that the similarity between them both, between the object in the image here and look, the object in the image here. First of all, look, the image is smaller than the object. And look at this one as well, the image is also, look, smaller than the object. So we can use the word diminished. So the image is diminished. Okay, the next one then, the difference. What is the difference between both those diagrams? Hopefully you can see that this one, the image is upright. And in this one over here, look, the image is upside down. So let's put that down over here. So the difference is going to be in convex, the image is inverted. That just means upside down. And for this one over here, for the concave, we're going to notice that the image is upright. .4. A person uses a lens to read the letters on the back of a coin. The image height of the letters of the coin is 9 millimeters. The magnification produced by the lens is 6. Calculate the height of the letters on the coin. Right, you should hopefully remember that the magnification is equal to the image height divided by the object height, yeah? Or the image distance divided by the object distance from the lens. So that means that the 6 goes here in the magnification. Right, now we've got this, 6. Now, what is the image and what is the object? Well, look, the image height is going to be this. So we've got the image, we're trying to find the object height, or the letters, the height of the letters on the coin. So we're trying to find O over here. So the image height is 9, the object height, we don't know, O over here. So therefore, just rearranging this then, so O is equal to 9 divided by 6. Therefore, it's going to be equal to 1.5 millimeters. That's my answer, 1.5 millimeters. Okay, the next one then. So let's scroll down for the next one. It's going to be question 2. Figure 4 shows the apparatus used to investigate the waves on a stretched string. The frequency of the signal generator is adjusted so that the wave shown in figure 4 is seen. So we're going to look, we have the signal generator over here connected to the vibration generator. And obviously it oscillates and you get this wave pattern being formed. The wavelength of the wave shown in figure 4 was measured to be 80 centimeters. What piece of apparatus would be suitable for measuring the wavelength? To measure that distance, obviously, hopefully you recognize that we're going to use the piece of apparatus of a meter rule, yes? So a meter rule over here. That's going to be my answer. Write down the equation which links frequency, wavelength, and wave speed. The wave speed is equal to the frequency multiplied by the wavelength. Excellent stuff. Next one is going to be 2.3. The string in figure 4 vibrates at 55 Hertz. Calculate the wave speed of the wave shown. Right, so you want to look at the wave speed. Wave speed is equal to the frequency times by the wavelength. The frequency we're given, it's going to be 55. Now the wavelength, right. A lot of people don't understand where I'm going to get the wavelength from here. But look, in order to spot this, I've always told kids to just ignore the dashed bit right now. And this up and down, you've gone up and down right now. So we've gone up and down. This corresponds to one wave. Because one wave is this, up and down here. So just ignoring the dash bit for a minute, you're just going to look at this bit over here, which looks like this. Hopefully you can recognize that is one wavelength. So that is going to be one wavelength. So this 80 centimeters is equal to one wavelength. So 80 centimeters is equal to the one wavelength over here. Don't forget, we must convert the wavelength into meters. So the wavelength is equal to 0.8. Excellent stuff. Right, so scrolling down, this one's going to be 55 times by 0.8. We're going to get the answer of 44. So the answer is going to be 44 meters per second. 44 meters per second. Next one then, let's go for 2.4. The frequency of the signal generator is increased. This makes the wavelength of the wave change. So you increase the frequency. So what's going to happen is when you increase the frequency, I'm just going to redraw that over here. What happens is, so there's the little bridge initially. So if you look at that diagram at the top, there's the bridge there and the frequency, the vibration generator is over here. If you increase the frequency, you're going to see more waves on there. So you're going to see more waves. So I'm just going to draw, imagine we have, this is the vibration bit over here. You're going to see more waves. Okay, we're going to see more waves over here. So more waves are seen. Describe how the apparatus could be adjusted to show one complete wave without reducing the frequency. So how are we going to show one wave now? So look, how are we going to show one wave? Look, if I take this wooden block over here, if I move it to the right, if I take the wooden block and I move it to the right over here, then obviously this will once again show me one wave over here. That will be one wave over here. So therefore, look at this diagram. All we can do is this. If we want to show one wave, if you increase the frequency over here, we move the wooden bridge, the movable wooden bridge, to the right. So the answer is going to be we move move wooden bridge to the right. Yeah, okay. Right, the next one. So that's 2 marks over there. 2.5. A student wants to investigate how the wave speed on a stretched string depends upon the tension in the string. Describe a method the student could use for this investigation. 4 marks. So you're trying to see how the tension affects the wave speed. Yes, how tension affects the wave speed. If you look at the diagram, what we're going to be doing is the following. You're going to be increasing the mass over here because this will increase the tension. So don't forget the tension, that pulling bit, you can only increase it by adding the masses over here. So by adding the masses on top of here, you're going to be increasing the tension here. So what about our method then? What we're going to write down for our method, first of all, we're going to have to add masses at the bottom, at the end of the pulley. So number one, I would say we're going to add masses to end of pulley. Now you've added the masses to the end of the pulley. What's going to happen is then obviously as you add masses to the end of the pulley, then you're going to increase the frequency. Then you're going to increase the frequency over here until you see this pattern. Yeah, you see this pattern over here, or one wavelength. So we're going to go back over here. So we're going to go for add masses to the end of the pulley. And number 2, you're going to increase the frequency until first wave pattern is observed. First wave pattern is observed. Okay, and then as you've done that, now you've done that from here, then you're going to have to obviously, don't forget, we're trying to find out the wave speed. So we obviously need to do the wave speed is equal to frequency times by the wavelength. I can work at the wavelength by taking that measurement. So measure the wavelength using the meter rule once more. And then finally, we're going to obviously calculate the wave speed using the equation. So calculate the wave speed using formula V is equal to F times by lambda. Yes, hopefully you're happy with that. Now you've done that, don't forget, you've done that, and then you're going to repeat again for different masses, because then you are going to be changing the tension. So we're going to then finally, last point is going to be add masses and repeat. So add masses and repeat. Next one, it's going to be 3.1. The driver of the vehicle sees a hazard on the road. The driver uses the brakes to stop the vehicle. Explain the factors that affect the distance to stop a vehicle in an emergency. It's 6 marks. Hopefully you can remember that it's about the stopping distance. If you've forgotten, it's the stopping distance is equal to the thinking distance plus the braking distance. Yes, the braking distance. I always get that spelling wrong. So the factors affecting the thinking distance are going to be factors affecting your reaction time. So the reaction time of the driver can be affected by multiple things. So it can be affected by alcohol consumption, tiredness, age, distractions, and obviously intoxication. Excellent. So look, we've talked about all this affecting your reaction time, and then from here, a last statement I'm going to put down is if the longer the reaction time, the greater the thinking distance. Okay, right, so those things all affect the reaction time. Also the speed, so the speed. So the speed also affects the reaction time. As the faster you are going, the longer it takes to stop. Okay, right, so we talked about the factors affecting the reaction time. What about the braking distance? Well, the braking distance is everything physical. So the factors affecting the braking distance, are going to be, guys, like the condition of the brakes, the condition of the road, the weather, the friction on the road as well, and obviously the speed again. So don't forget, those are all going to be physical conditions here. So it's going to be tire condition / brake condition, icy roads, and obviously all of these things. So these factors affect the friction. And obviously it's going to be the lower the friction, the further the car will travel. The lower the friction, the further the car will travel. Okay, right, the next one then. Let's go for it. So 3.2, write down the equation that links force, work done, and distance. So work done is equal to the force times by the distance. 3.3, calculate the braking distance. So work done divided by force is equal to the distance. So the work done is 900,000 joules divided by 60,000 over here. That's going to be the distance. The distance is going to be 15 meters. Excellent stuff. The next one, the greater the braking force, the greater the deceleration of the vehicle. Explain the possible dangers caused by a vehicle having a large deceleration when it is braking. Right, so if you have a large deceleration when it's braking, what's going to actually happen here? Well, think about the brakes, yes? So the brake pads will press. What will happen is the brakes could overheat. So the brakes could overheat. And obviously that can make you lose control of the vehicle, so it can cause the car to skid. cause the car to skip over here. 4.1, draw the magnetic field of the solenoid. Okay, so first let's draw the field lines. So we'll have one field line going directly through, another one over here, there we go, and the other one's going in as well. Don't forget the magnetic field runs through the solenoid and comes out over here. Now, which way are those lines going? Which way are those lines going? Don't forget, we can imagine you look at the side of this tube, you'll see a circle, yes, and look, the current's going up this way and down that way, just on this side over here, and therefore this is going right. So there, don't forget, then you can remember that it's going to be like the N, yes, this will be the north, yes, so this one matches up, this one will be the north over here. So this is the north pole, and therefore the lines go out of the north. If you're struggling in this one, watch my video, I'll put it in the description, in which we can look at how to determine which way the field is going inside a solenoid. So if you look at this one over here, look at this circle over here. So it's going down the right hand side and up on the other side. This one is the S over here, so this one is the south. So it goes in this side over here and out this side over here. So this is the north and this is the south over here. Now, 4.2, it's going to be figure 6 shows two iron rods placed in a solenoid. Explain why the iron rods move apart when the switch is closed. Why do they move apart when the switch is closed? Well, when you close the switch, what happens is current flows through the solenoid, yes? And therefore, this becomes magnetized, and so does the other one. So what happens is that both the rods become magnetized. So both rods become magnetized. And as they both become magnetized, they will have the same polarity, and therefore they will repel each other. So therefore, they repel each other, repel each other as they have the same polarity. Excellent stuff. Okay, next one. Let's go for a student investigated the strength of an electromagnet. The student investigated how the strength depended on the current in the wire, the number of turns of the wire around the iron core. Figure 7 shows the equipment used over here. So figure 7 shows the equipment used. So look, iron core, steel plates, the weight over here, ammeter and the power supply. Right, hopefully you can see that. Greater the current here, the more it can attract this steel plate, and therefore the more weight it can hold. The student measured the strength of the electromagnet as the maximum weight the electromagnet could hold. There we go, so we've got a table here. Current over here increasing, number of turns increasing, and the maximum weight it can hold in newtons. Explain why the method used by the student is not valid for the investigation. So why is it not valid for this investigation? Why is he not going to have a valid set of results? The reason why is because they are changing the current at the same time they are changing the number of turns. So it's difficult to say what is actually causing the effect here. So it's difficult to actually make a solid conclusion. So the reason why is because multiple variables are being changed at once. At the same time. And therefore it's not possible for you to determine what the effect is of one of the variables. So therefore, impossible to determine the effect of one of the variables. Of either variables. Next one, let's go for the next one over here. Let's go for the next one over here. A second student repeated the investigation using the same equipment. Figure 8 shows the student's results, the second student's results. So right, look, as you can see, they've got weight in newtons, they've got 30 turns of wire, 20 turns of wire, and 10 turns of wire. How does increasing the current in the wire affect the strength of the electromagnet when the electromagnet has 30 turns of wire? Well, hopefully you can see that as you increase the current, the weight that you can hold increases. So the strength increases. So the strength increases. Yes, and look for the first, when you're looking at this one over here, until it reaches a maximum value. The strength increases until it reaches a maximum value. Excellent stuff. Right, the next one from here, let's go for 4.5. How does increasing the number of turns of wire from 10 to 20 affect the strength compared to increasing the number of turns from 20 to 30? So when you're comparing 10 to 20, so we're comparing these two, compared to 20 to 30. So obviously we can see there's a greater change from 10 to 20 than there is from 20 to 30. So we can put that down over here. There is a greater change from 10 to 20 turns than from 20 to 30 turns. 5.1. The light from distant galaxies shows redshift. Complete the sentence. The term redshift describes the observed increase in the what. Hopefully you can remember that the wavelength is going to increase in the wavelength of the light from distant galaxies. The Big Bang Theory is one model used to explain the origin of the universe. How does the Big Bang Theory describe how the universe, when it began? It was hot plus dense over here. Hot and dense over here. Next one. Figure 9 shows data scientists have calculated from measurements of redshift. Speed of the galaxy away from Earth and distance away in terameters times 10 to the power of 12. Right, okay, now from here it says describe the relationship between the speed of a galaxy and the distance the galaxy is from Earth, there to there. What happens is, obviously they are directly proportional. So the answer is going to be directly proportional. So this answer is going to be directly proportional. 5.4. Which of the following is the same as 6 times by 10 to the power of 12 terameters? Terameters simply means times 10 to the power of 12 meters. It's the same thing, yes? Don't forget tera is times 10 to the power of 12. So therefore, if you have 6 times by 10 to the power of 12, yes, timesing that by obviously 10 to the power of 12 meters. Therefore, indices, look, so 6 times by 10 to the power of 24 meters is this one over here. That's going to be the answer. 5.5. Explain how the data from figure 9 supports that the universe began from a very small region. So how do you know it's from a very small region? Alright, so if you're looking at this graph over here, hopefully you can see that as the distance from the Earth increases, you can see that the speed of the galaxy is actually moving faster and faster. So that's the first observation we can make. So we can put that down over here. It's going to be equal to, so galaxies further away. So galaxies further away. So further away are moving the fastest, That's the first thing. Yeah, so galaxies further away are moving the fastest. So obviously if the galaxies further away are moving the fastest compared to the ones which are closer, they're moving slower, that tells you that the universe is expanding. So this tells us that the universe is expanding from a very small region. Excellent stuff. Okay, the next one is going to be over here. 5.6. The Big Bang Theory suggested that gravity would slow the rate at which galaxies move away from the Earth. New observations suggest that distant galaxies are moving away from the Earth at an increasingly faster rate. So if they're moving away at an increasingly faster rate, what do these new observations suggest is happening to the universe? So if they're going to be moving away at an increasingly faster rate, that tells you that the rate of expansion is increasing. So the rate of expansion is increasing. 5.7. New observations and data that do not fit existing theories should undergo peer review. Give one reason why peer review is an important process. Why do you want to have peer review taking place? Why does one scientist want to look at the work of another scientist? Is obviously to avoid bias. Yes, you don't want your one scientist to maybe possibly be lying. So avoid biased data. That's going to be the key thing here. So to avoid biased data. Avoid biased data. The mark scheme also accepts detecting false claims, detects inaccurate data, verifies new data, provides consensus as well. All of those are acceptable, but I'm going with to avoid biased data. 5.8 it's going to be. The Andromeda Galaxy is moving towards the Earth. Describe how the wavelength and frequency of the light from the Andromeda Galaxy seems to be changed when viewed from Earth. Now this one's moving towards us. It's not redshift, it will be blue shift because it's moving towards us. So as it moves towards us, we know that the frequency will increase. So the frequency will increase and the wavelength, because they're inversely proportional, will decrease. Excellent stuff here. The next one then, it's going to be 6.1. An adult of mass 80 kilograms has more inertia than a child of mass 40 kg. What is inertia? Okay, so inertia simply means that it's when an object simply wants to remain in its natural state. That means either if it's at rest, it wants to remain at rest, or if it's moving, it wants to continue moving. So let's put that down here. So it's the tendency of an object to remain in its initial state, either stationary or moving. Okay, the next one, 6.2. A teacher demonstrated that the idea of a safety surface. She dropped a raw egg into a box filled with pieces of foam. The egg did not break. Okay, explain why the egg is less likely to break when dropped onto soft foam rather than the concrete floor. Right. When you drop it in, what's going to happen? Well, when you drop it into the foam, it increases the impact time. So yes, it will increase the impact time, yes? So the impact time increases. So the impact time increases. Hopefully you remember this formula, that the force is equal to the mass times by the change in momentum, change in velocity over time taken. So look, if you increase the impact time, therefore, what happens is the rate of change of momentum decreases. So look, it changes momentum. Don't forget, it's moving at the start, it has momentum, and obviously it stops moving. The rate at which that momentum is changing decreases. So the rate of change of momentum is decreases over here. And therefore what happens is the force is reduced. And therefore the force is reduced. Therefore, the force on egg is reduced. Okay, right, the next one from here, it's going to be figure 11 shows a child on a playground swing. The playground has a rubber safety surface. A child of mass 32 kg jumped on the swing. When the child reached the ground, she took 100 milliseconds to slow down and stop. During this time, an average force of 800 newtons was exerted on her by the ground. Calculate the velocity when she first touched the ground. So she's on the swing, and obviously it moves off, yes, and what happens is you touch the ground. Okay, so first of all, when she first touched the ground, what's going to happen? Obviously she was moving, and she's going to slow down. So we're going to be looking at the following formula. Force is equal to the mass times by the change in velocity divided by time taken. Okay, so now from here, the force is going to be 800, but it's going to be negative 800. The reason why? Because it's going to be in the opposite direction to the motion. Don't forget, it's going, the force is going to try and pull them back. So that's the reason why the force is going to be negative. So it's minus 800. The mass over here was going to be 32. The final velocity was 0, yes, because it stopped moving at the end, minus the initial velocity. The initial velocity was how much? You're trying to work that out. Divided by the time taken is going to be 180 milliseconds, converting this into seconds. So it's going to be 180 times by 10 to the minus 3 over here. So now rearranging it, we're going to go for 800 times by 180 times 10 to the minus 3 divided by 32. I'm going to get the answer of 4.5 over here. So it's 4.5 meters per second over here. Don't forget, the force was in the opposite direction. That's why this was minus, therefore making this one positive at the end. So the answer is going to be 4.5 meters per second. 7.1. Which one is the correct box? Hopefully you recognize that they all travel at the same speed because they're all electromagnetic waves. But obviously the frequency is increasing. So it's going to be this one over here. 7.2. Explain how the properties of X-rays make them suitable for medical imaging. Well, first of all, for medical imaging, what happens is the X-rays can penetrate through the skin. Yes, so X-rays can pass through soft tissue. So let's put that down. X-rays can penetrate through soft skin and slash tissue. There we go. And obviously, but absorbed by bone. But absorbed by bone. A student investigated the infrared radiation emitted from the sides of a hollow metal cube. The sides of the cube are different colours or textures. Figure 13 shows the equipment used. So kettle filled with hot water, hollow metal cube, water in, shiny black surface, shiny silver surface, matte white surface, matte black surface over here. We've got a ruler over here. The infrared detector uses the infrared to give a temperature. So this will obviously emit infrared, and we're going to measure the temperature here. Suggest so boiling water is a hazard in this investigation. Suggest how the risk of harm could be reduced in this investigation. It's simply going to be, it simply can be, do not touch the cube. Do not touch the cube. We also accept you can wear gloves. Maybe complete the investigation standing up. In case it falls on the bench, you can easily move away. Or you could use slightly cooler water. All of those are acceptable. 7.4. What is the control variable in this investigation? So what was the control variable in this investigation? Well, look, what must you keep the same throughout the whole thing? The distance of the infrared detector to the actual block over here. So the distance between, the detector and each cube surface. Excellent stuff. Right, next one's going to go for 7.5. The 4 temperature values in table 2 cannot be used to show that infrared detector gives precise readings. Right, how would it not be precise readings? Why is it not precise? Well, don't forget, in order to show precise readings, you've got to have at least repeats of each measurement. So you should have actually got 68, maybe 70. So you're meant to take multiple repeats, and then you're going to check if they are close together or not. So that's the reason why. So again, the reason why is because multiple repeats for each surface have not been recorded. So look, multiple repeats of each surface have not been recorded. So you need to do multiple measurements of each one to show how close they cluster to each other. So guys, from here, you want all the repeat values to be close together. Therefore, it will tell you if it's going to be a precise set of measurements. If you're struggling on the word precision or accuracy, check in the description. I've got a whole video on precision and accuracy as well to help you. 7.6. The student looked at the data in table 2 and concluded a black surface always emits more infrared radiation than the white surface. Explain how using an infrared detector with a resolution of 1 degree Celsius would have affected the student's conclusion. So they're saying that the black surface always emits more than a white one. If they used a resolution of 1 degree Celsius, how would that affect the results? Well, look, if it was 1 degree Celsius, well, what happens is this one will round to 68, this one will be 66, this one will also be 66, and then this one will over here would be what? 28. So don't forget, it's the resolution right now. It just means decimal places. Explain, so what will happen to this statement then? A black surface always emits more. Well, clearly not. It's not always going to be emitting more. So yes, on the previous set of data, the black surface always emitted more. But now, if you use a resolution of 1 degree Celsius, basically it would mean that the student could not conclude that black surfaces emitted more radiation. And the reason why is because the matte white and the shiny black are the same temperature now. Because matte white and shiny black are the same temperature. Of 66 degrees Celsius. Albedo is a measure of the amount of solar radiation reflected by an object compared to the solar radiation incident on the object. A perfect reflector has an albedo value of 1. A perfect absorber has an albedo value of 0. What is the albedo value of a perfect black body? So hopefully you remember that a black body absorbs all radiation into it and emits it, yes? Nothing to do with reflecting, yes? Absorbing and emitting. So it's the perfect absorber, therefore it's going to be 0. So it's this one over here. Figure 14 shows 2 points A and B. Okay, there we go. We've got a cloud, point A and point B. The average albedo value for the Earth is 0.3. The albedo value of thick cloud varies between 0.6 and 0.9. Okay, so it's 0.6 and 0.9. So 0.6 and 0.9. So therefore, it means that it's a look. It's going to be a good reflector. So the cloud is going to be a good reflector. Let's put that down. So good reflector. So that's going to be the cloud over here. At night, the air at point A cools faster than the air at point B. Explain why. Well, hopefully you can recognize that the Earth's surface will emit heat. The Earth's surface will first of all emit the heat. Over here, yes, the Earth's surface will emit the heat on both sides over here. Okay, so if the Earth's surface is going to emit the heat, what's going to happen is right now, that heat will travel upwards, but look, the cloud will reflect the heat back down over here. So what will happen is, obviously, B will actually cool down slower. A will cool down much faster because the heat from the Earth's surface can leave it just easily going upwards over here. B will take a long time because the heat is going to be reflected back down to B, and therefore it cools at a slower rate. Okay, so the first point is quite tricky in the mark scheme. It's going to be that at night, so obviously at night, first of all, there's no more radiation coming down. There's no more heat coming down. At night, the Earth's surface will emit more heat, more radiation than absorb radiation from space. So that's the first thing to note, that yes, there's more heat going to be leaving the Earth's surface than coming back down in. And then we're going to talk about the cloud then is going to reflect the heat back down. So the cloud reflects the radiation back to B. And obviously at point A then, there's a greater proportion of the radiation leaving the Earth's surface. So at A, there is a greater proportion of heat leaving the Earth's surface. And obviously, therefore, it cools faster. And therefore, cools faster. That one is a tricky question, fair enough. I give you that, it's a tricky question. 8. An aeroplane is 4,000 meters above the Earth's surface. A skydiver jumps from the aeroplane and falls vertically. Figure 15 shows the distance the skydiver falls during the first 12 seconds after jumping. Okay. Figure 16 shows part of the free body diagram for the skydiver 3 seconds after jumping. So 3 seconds after jumping over here. Right, complete the free body diagram for the skydiver. So obviously, it has not reached terminal velocity yet. It hasn't reached a constant velocity. That's over here. So therefore, I'm going to have to draw the weight arrow going downwards from here. And it has to be greater. Obviously, use a straight line, use a ruler. It has to be greater than the air resistance one over here. So this one's going to be the weight going down. This is going to be the weight over here. Okay, so now, next question. Explain how the changing motion of the skydiver in terms of the force acting on the skydiver. So if you've forgotten, what happens is you have the skydiver initially. Initially, there's the only thing acting is the weight. But as it falls down, yes, what happens is the air resistance starts to build up. So air resistance starts to build up. Eventually, they both balance out. The air resistance balances out with the weight, and therefore it reaches terminal velocity. So look, if I have a velocity time graph, we know it will reach terminal velocity over here. That's the last one over here. So from here, let's put this all down into words. So let's say that initially air resistance is less than the weight. So the skydiver accelerates. But then air resistance builds up. As velocity increases. And therefore, eventually, the forces balance out. And as the forces balance out, now the skydiver moves at terminal velocity. Excellent stuff over here. Next one, 8.3. Use figure 15 to determine the speed of the skydiver between 7 and 12 seconds. To work out the speed, it's going to be the distance divided by time. So the change in that distance over there and there, so it's 200 there, and over here it's 450 divided by the time. So 12 minus 7, it's going to be 5 over here. Yes, so therefore speed is equal to distance divided by time. So it's going to be 450 minus, so it's 250, yes, this minus this, divided by 5. We're getting the answer of 50, so the answer is going to be 50 over here. So the 50 meters per second. So obviously put all that writing down at the bottom over here. So therefore over here, I'll put that down over here. So it's going to be 450 minus 200 divided by 5. So therefore it's going to be 250 divided by 5, which is going to be 50. There we go, 50 meters per second. Obviously you have to write on the graph to show that you've actually used those points over there. Okay, right, the next bit. 8.4. In 2012, a skydiver jumped from a helium balloon 93,000 meters above the Earth's surface. The skydiver reached a max speed of 377 meters per second. Right, jumping from 39000 meters allows the skydiver to reach a much higher speed than the skydiver dropping from this much. What is the reason why? Why can you reach a higher speed? So what is about the altitude? So the higher up you go, hopefully you recognize that there's going to be, obviously, less air pressure. So the air is less dense. So the higher the altitude, the air is less dense. The air is less dense. If the air is less dense, then as you fall through it, it becomes harder for the air resistance to build up. So therefore, the air resistance experienced is less, and therefore it takes longer to build up. So therefore, the skydiver can accelerate for longer. The skydiver can accelerate for longer. So obviously there's less air resistance building up against you, so you can accelerate more. And then obviously eventually you can reach a greater terminal velocity. So therefore the skydiver can accelerate more and therefore reach a higher terminal velocity. Excellent stuff. Okay, next one. Let's go for 9.1. Table 3 showed the frequencies of the hearing ranges of 5 different animals. Cat, dog, chicken, gerbil, horse. Which one of the animals, table 3, would not be able to hear ultrasound? Ultrasound is 20 to 20,000 hertz. Yes, that's ultrasound range. So obviously it's the chicken, can't hear it. So it's going to be the chicken. So there you go, look. For 1 mark is going to be the answer of chicken. The next one, it's going to be figure 17 shows the ultrasound being used to detect a hidden crack in a solid aluminium object. The transmitted and reflected pulses of ultrasound are shown on the screen. Okay, so look, transmitted pulse, and then the reflected one back, and there's another one over here. Right, which of the following is the same as 2 microseconds? Micro stands for times by 10 to the minus 6. So it's going to be, there we go, minus 6, it's this one over here. 9.2, it's going to be this one over here. Then 9.3, it's going to be, the ultrasound travels at 6,300 meters per second in aluminium. Determine the depth of the crack below the top surface of the aluminium. Right, so we want to work out the depth of the crack and give your answer to two significant figures. So in this question right now, you don't forget the transmitter sends out a wave. Yes, it hits this and goes back. Yes, the time taken for that wave to go down and up is this time here. It's that time there. The other one, this other pulse over here, it's when the wave goes down to the bottom and goes back up again. Yes, back to the receiver here. Obviously, this one is longer because it takes longer for you to make that all the way to the bottom and all the way back up again. The question is asking you a distance to the crack, just this distance here. So hopefully you recognize that speed is equal to distance divided by time. Therefore, distance is equal to speed times by time over here. The speed of the wave, the speed of that wave, yes? It was given to us in the question. It was going to be 6,300. So it's going to be 6,300 over here. So from here, it's going to be 6,300. So 6,300 times by the time taken. So don't forget the time to go down to the crack and back. So that's, look, we've got 1, 2, 3, 4 divisions. So 4 divisions over here. Each represent 2 microseconds. So 4 divisions, so 4 times by 2 times by 10 to the minus 6, because each one is going to be 2 microseconds. It's 8 times by 10 to the minus 6 seconds. That's the time taken for it to go there and back. So if I want the time taken just to the crack, don't forget that's the total time, I need half of that. So to divide that by 2, so the actual time taken to go to the crack, the depth of it, which is the time taken just to go there, it's going to be 4 times by 10 to the minus 6. So I divide that by 2 over here. So that's the time taken just to go down to the crack over here. So times by 4 times by 10 to the minus 6 over here. Let's see what our answer is. So 6,300 times by 4 times 10 to the minus 6. My answer, the depth, is going to be equal to 0.025. That's going to be my answer over here. Whoops, 0.252. But don't forget the question is asking me to round it to 2SF, so it's 0.025. So the answer is going to be 0.025. Obviously copy all that working out I did earlier into your answer here. 9.4, what is the function of the microphone? Is to convert the vibrations, into electrical signals over here. Next one, 9.5, explain how a moving coil microphone works. Right, so look, the vibration goes in and you're generating the voltage. So hopefully you can remember that this is the generator effect. So this one will be the generator effect because you are generating that voltage here, or generating the potential difference. Right, so what happens is, number one, the sound causes the diaphragm to vibrate. So the diaphragm vibrates. So sound causes the diaphragm to vibrate. Yes, the diaphragm vibrates. This causes the coil to vibrate as well. The coil to vibrate. Okay, so this causes the coil to vibrate. So that coil then starts to move in and out of the magnetic field. So don't forget there's a magnetic field here, this permanent magnet over here. This coil is now moving within it, and therefore a potential difference is induced. And therefore the coil experiences a changing magnetic field. A changing magnetic field. And obviously, guys, this is the generator effect. Therefore, a potential difference is induced in the coil. And I would say, everyone, guys, make sure you understand the generator effect. I've got a whole video on the microphone and how it works using the terminology of the generator effect. Please make sure you watch that if you don't understand this one, because this is just one question. But truly understanding the generator effect will enable you to tackle this question as well. 10. Figure 19 shows the back of a lorry. The lorry is used to carry horses. The ramp is lowered by pulling on the rope or by pulling on the handle? The hinge acts at a pivot point. Explain why it's easier to lower the ramp by pulling on the rope rather than by pulling on the handle. Why is that possible? Well, look, guys, if you know the hinge point is over here, look, this distance is smaller than this distance going all the way up here to the top. So therefore, you've got a greater distance from the pivot point. The distance between the rope and hinge is greater than the distance between the handle and the hinge. The handle and the hinge. You should be thinking of moments here, yes? Look at that perpendicular distance over here. And therefore you need less of a force. So therefore less force is needed. Less force is therefore needed. Okay, so next one. When the ramp is lowered, work is done to stretch a spring on the side of the ramp. Elastic potential energy is stored in the stretched spring. Right, okay, so over here we've got the ramp, we've got the spring over here. With the ramp horizontal, the moment caused by the weight of the ramp, okay, the weight of the ramp, this one, is 924 Newton meters. So look, pivot point is there. This moment pulling it here is going to be 924 Newton meters. Don't forget, a moment is going to be the turning force here. The spring is stretched by 0.25 meters. Calculate the elastic potential energy stored in the spring. Elastic potential energy is equal to a half K E squared. Right? That's the formula. Right, but we don't have K. We don't have K. But it's something about moments here. So look, we know there's a pivot point here. We know that for the pivot point we know that for the ramp to be balanced, the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So therefore, we can say that the anti-clockwise moment is equal to the clockwise moment. Yes, that's the first thing we're going to do. So the anti-clockwise moment, look, this one is pulling it, the whole ramp, anti-clockwise. This is an anti-clockwise moment. This one is trying to spin it, spin the ramp clockwise. Okay, so the anti-clockwise moment, they've given it to us 924 Newton meters. The clockwise moment is going to be the force times by the perpendicular distance to the pivot point. So the force, we don't know, what that force is. So we'll just put this over here as F. We don't know what that force is. The perpendicular distance is 0.15. Now, therefore, F is equal to 924 divided by 0.15. So it's going to be 924 divided by 0.15. The answer of the force is going to be 6160 newtons. So now we know the force pulling upwards is going to be 6160 newtons. Right, now you might be thinking, hang on a minute. Now we know the force. How's that going to give me K? Well, we can use another expression to work out K, which is going to be the Hooke's law one. Force is equal to K times by the extension. We've got the force 6160 is equal to K and that divided by the extension 0.25 is equal to the value of K divided by 0.25. So the value of K we're getting is 24640. Right, it's a hard one. This question's really hard. So now we've got the value of K, we can finally use it to work out the elastic potential energy. E is equal to a half times by 24640 times by elastic potential energy 0.25 squared over here. So it's going to be 24640 times by 0.25. You have to square that, divided by 2. I'm getting the answer of the elastic potential energy is equal to 770 joules over here. Excellent stuff. Right, okay, we're done for another session. Obviously, this is a past paper, me just walking you through it. And if you don't understand any of the questions that we've covered today, please look at that content again, yes? A detailed understanding of the content will help you with any question that's coming up. The misconception is that loads of kids, they think they're going to do a past paper and that same question comes up. Obviously not. Every year, the paper changes. So if you make sure you master the content, you should be fine with any question that it can throw at you. And that's it for another session of Ceerazzledazzle Physics. Make sure you hit the like and subscribe button to keep my channel going. Comment below if you have any queries. I'll do my best to answer them. I know it's a tricky paper, guys, but obviously put the work in and you should be fine. Ciao, ciao, and goodbye.